Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. Let's continue our discussion of this piecewise defined functions as we apply it to finite element methodology. We were talking about the piecewise, and then there's a certain amount of discontinuity at the element boundaries. So how much that is acceptable? We want to make it as relaxed as possible so that we can apply very, very simple function. So what we are saying here is that, just to recall, if you want to integrate something like a fx, so as such the theory says that this integrand fx has to be continuous and well defined. That means that single valued in the whole function. So f has to be continuous. Okay, so this is what we are saying, and well defined or single defined, single value. So but what we want to do is that relax this requirement, and then let us see if there is a discontinuity. As such we cannot apply. If there is a discontinuity, such as somewhere here, let us say, let's just take as not that not necessarily a curved thing. So if you want to do this, so now if there is a discontinuity, so at point C here, and we call it as 1, 2, 3. I think we'll just call it as 1, 2, 3. Same thing here, 1 to 2. Yeah. So if it is, if there is a discontinuity at 2, then so as such we don't allow it because the function is not single valued. So what we would like to do, so this, the branch of mathematics which discusses this thing is the Sobolev spaces, where they have piecewise defined functions and then they talk about the integration and so on. So here what has been done is that to make it regular or a continuous function, so they smoothen this part here by another curve here. So let us say this is x2 minus delta, and this point is x2 plus delta. So over a small zone minus delta to delta. So what we did is that we have drawn another curve here, so that now the modified f here, this is a modified here, and then this is the original f here, and the original f here, and then this is the modified here. So this is a modified one, approximated. Okay. So what they say here is that if you look at the integration of this one, if you look at the integration of this f here, say f dx, x1 to x2 minus delta, and x2 minus delta to x2 plus delta. So this modified one, and this is x2 minus delta to x3. This is the integration if you are talking about. So what we did in this x2 minus delta to x2 plus delta, we just approximated it by regularized it as a single valued function. And then if you look at this one, so here, so this as the delta becomes 0 and 0, then what happens to this integration here, the second integration? So as in the limit, as delta tends to 0, so this becomes here. Let's call this as, maybe we'll call this as f1 here, and f2, and in between it is f delta. Okay, we can just, for the sake of thing, so we'll just make it as f1 and f2. So the whole thing now, so the middle integration, which I shown it as shaded, so that's going to be 0, and this f1 simply becomes x1 to x2, and middle one is 0, and this is f2 x2 to x3. Okay, so what essentially it is saying is that if you need the integration of the whole function, so you can integrate it over the domain omega 1 and omega 2. So what this says is that, so that means that this is equal to, so your original f x1 to x3 is simply tends to limit, okay, f1 x1 to x2 okay. So this is essentially what is that the integration of this one here, we can avoid the point here, and then you can just integrate it between x1 to x2 and x2 to x3. So that is equal to the integration of f over the complete domain. Okay, over the complete domain, you can just do the piecewise integration, and the total integration will be equal to the total integration value of f x1 to x2. So this is a very important, this is a very important result which is applied to FEM. Okay, so that means that if you are doing, say, d by if you are doing d phi by dx integrated over the whole domain. Let us say terms involving d phi by dx. So according to this one, so it is simply equal to omega 1 d phi hat of 1 plus on omega 2. So this is a very important result, saying that if you want d phi by dx to be integrated over the whole domain, so it's essentially equal to, so d phi hat by dx as defined in 1 integrated over omega 1 plus d phi hat by dx of phi 2 as defined in omega 2. So what happens at the inter-element boundary, that is at x2, is not going to enter our calculations. Okay. So essentially, finally, if I say that, so this is true only when there is a finite discontinuity. If the discontinuity is infinite, so this kind of approximation cannot be done. For example, if there is something going here this way and something coming to the top from infinity, so the integration is not at all defined. So these integrations are possible only for, so this is possible only at finite discontinuities. Okay, so this is a very important result, saying that you can still do d phi by dx. Though d phi by dx has a finite discontinuity, the integral over the whole domain is equal to the integral over each subdomain separately. So if this is the one, if d phi by dx is having a discontinuity, what kind of function we call it? A finite discontinuity is allowed in d phi by dx. So if you look at that earlier one, so if you allow a d phi by dx so this is d phi by dx. So in the first part you have d phi hat by dx of 1 and this is d phi hat by dx of 2, 1, 2, 3. So this, if I just do the backward calculation, so this is piecewise defined linear functions. There is a continuity here, but if you come to the d phi hat by dx, so there is a discontinuity. But as we talked about all these theories, so then what we are saying is that if you have I'll write it appears in like this, then the phi hat, then phi hat overall has to be what kind of function which we call here. So this is a, so it is nf phi hat is what? C0 continuous. Okay, so this is a very, very important result here. So that means that if d phi hat by dx is appearing in the integrand like this one, then the phi hat has to be C0 continuous. So this is a C0 continuous function. C0 continuous means the function is just continuous, but however, the derivative may have a discontinuity, a finite discontinuity. That's important. So finite discontinuities are allowed as per the mathematics, the Sobolev space theory. And then, so that means that this derivative constraint on the function has been definitely reduced, and then it works. So just as a offshoot of this one, so let's if you have a, let us say, just to extend this one, extending that one, extending this result. So if d square I hat d square now appears in like this, okay, then what kind of function which we require here? So that means that d square we can have finite discontinuity in d square. So if there is a finite discontinuity in d square, that means that in this, so that says that d phi hat by dx, d phi hat by dx has to be continuous. So if the derivative has to be continuous, so that means that it's one more than this one. So if the derivative is continuous, so then so this means that the function phi hat has to be C1 continuous. Okay, so this is the important observation. So this is one more order here. The requirement is one more order here, and so that means that, so if you have a d square appearing in the integrand, then d square can be allowed to have a discontinuity. So that means that d phi by dx should be continuous. Okay, finally. So this can be extended to, say, an auth derivative appearing in the like this one. Then what kind of requirement is there for phi? Now we can extend it. Then phi has to be how much? So CR minus phi hat has to be CR minus 1 continuous. So this is exactly, this is an extension from here to here to here. So that means that if you have an ortho derivative, then the phi hat has to be CR minus 1 continuous, means that the ortho derivative may have a finite discontinuity. So that is allowed up to that point. Okay, so that's the approximations or even the weak form of weighted residual statement. So gets a very special significance in the sense that if you have L as a certain derivative R, then if you go for the weak form, so that is reduced to maybe R minus 1 or even further down, then the requirement on phi hat is further reduced. So this is going to give us a very solid foundation why we go for the weak form and why we go for the piecewise defined functions. So this gives a very solid background for finite element approximations. Okay, if you understand this one, so let us just get to some simple example. Let's try to explain this with respect to a one-dimensional. So now let's illustrate it with respect to the one-dimensional some problem here. And before that, so let's look at one-dimensional of d square phi over dx square minus phi is equal to 0 in x is equal to 0 to 1, and then with some boundary condition. So that I think we'll take it up a little later, but anyway, if you want, just for the sake of completeness, I will write it as phi a at x is equal to 0 we'll come to this as we go on. So the question now is that, so what kind of approximations? So if you look at the weighted residual statement, and in fact I also need the weak form of this residual statement. So the weighted residual statement looks like this one. So together with, maybe we can include the boundary conditions, but at this moment, let's not worry about that. And so this is, so the integrating it further, we get the weak form, partial integration. So we get so this is the bounded term, and we have minus okay. So this is the weak form here. So if you look at this one, what we require is the evaluation of this term. So if you look at this evaluation of this term, dwi d phi hat by dx, so where phi hat is the approximation here, and we can divide this interval into, let us say, some 3 subdomains. Okay, so what is that which we require here? So the requirement for phi hat, so we are going to define it piecewise. So what kind of phi hat we require? depends upon what kind of derivatives we have here. So the derivative here, the maximum derivative in this integrand is the first derivative d dx of phi hat. So which means that within the each element domain, we should be able to differentiate the function phi at least up to the first order. It should not become 0. So what else is that? This is the first derivative. So first derivative can be allowed to have a finite discontinuity. So which means that the phi hat has to be continuous. So if the phi hat is continuous, then the first derivative can have finite discontinuity. So what we mean by this one is just look at this one. So it should be at least d dx should be at least first degree polynomial. Okay, so phi hat has to be differentiable at least once in each element. Okay, so that means that the phi 1 has to be at least a1 plus b1x in omega 1, which is between x1 to. So we are defining it by different linear approximations. A2 in omega 2 and so on. So there are 3 here. So in each subdomain, we have defined it by a first degree polynomial. Okay, so that means that linear. So if you want to differentiate, you can differentiate it. It's very simple. If you differentiate this once, you get b1 or b2 or b3 in the domain 1, 2 and 3. So that's number 1. So that means that in each subdomain, it looks like this. In general, it looks like this one, which is linear. But then we also have another condition. So this is the general expression. The another condition here is that at element boundaries, so we have to have a continuity. So what does that mean? So that means this is phi hat 1 here. This is phi hat 2. This is phi hat 3. Right? So that means that for C0 continuity, so what we have here is that phi at 1 should be phi at 2 at x is equal to x2, right? So this is very important. So similarly, phi in domain 2 should be equal to phi in domain 3 at x is equal to x3. So for C0 continuity, so we should have this kind of condition. So there are 6 constants here on which we have these 2 conditions which have to be applied. Okay, so these have to be applied here, and to do that, so we have to apply some Lagrangian multiplier thing. So that kind of constraint we have to put it, or we can also do some other kind of jigglery and then try to arrive at this kind of linear approximation directly, not using A1, B1, A2, B2, A3, B3, but directly the functional values of this function phi hat at node 1, 2, and 3. So that's how we have to rewrite this approximation instead of writing it in terms of A1, B1, A2, B2, A3, B3. So for which we have to apply this condition can be circumvented by rewriting these coefficients in some other manner directly in terms of nodal values. So we'll stop it here. We'll continue this one tomorrow.